For this video, we will be talking about a variation of the MM1 model, and I will call this the MM1K model. What is the MM1K model? It's essentially your single server queuing system, so it's an MM1 model, but we now have a system capacity of K. What does this system capacity of K mean? It means that once you have K customers inside the system, then your queuing system closes and will not be able to accept customers coming in. A good example of an MM1K model is, for example, your drive-through model. Wherein, for example, let's say you have a McDonald's drive-through, and let's say the McDonald's drive-through can only accommodate 7 cars. Technically speaking, once there are 7 cars inside the drive-through, then any car that would like to enter the system will be asked to leave or come back later. Mathematically, mathematically, how does the rate diagram look like? Since this is your standard MM1 model, then it's essentially the same. Your rate diagram is essentially the same as MM1, except instead of the rate diagram going until infinity, it stops at k. Why? Because at state k, the arrival rate from k to k plus 1 is now 0. Okay, so technically speaking, we do have a limit in your rate diagram, no, as presented by your system limit k, and therefore your lambda sub n, which is equal to, in this case, lambda, but if this is only if your state is less than k, because once you reach a state of k and above, then, or in fact, when you reach a state of n equals k, then your arrival rate automatically becomes 0. Okay? Now, one implication that we will be using later on is that given that your lambda sub n is this, then lambda bar is different, no? And it is not equal to lambda. Okay? And I will be computing lambda bar later. Now, we will do the same thing. We will do the same process. We will get C sub n. C sub n is just the product of everything on top divided by the product of everything below. And therefore, as you can see, your C sub n is lambda over mu raised to n. And this is if n is less than or equal to k. And because we are getting the product of everything above, once n is greater than k, the arrival rate here is 0 already. Therefore, C sub n for n is greater than k is already 0. Because this is your C sub n, then your P sub 0 is still this, but substituted, we will get this. Our summation from n equals 0 to infinity will now be divided. No? So the summation from n equals 0 to infinity will be divided into the summation from n equals 0 to k plus the summation from n equals k plus 1 to infinity. No? But because C sub n, no, for n is equals k plus 1 to infinity is 0, therefore this is 0. Okay? So what we have here is the sum from n equals 0 to k of C sub n raised to -1. And when we expand the summation, it is just this. If you still remember your high school math, this is just the sum of a finite geometric series. And we do have a formula for this. The sum of a finite, not infinite, but finite geometric series is this. So 1 minus the ratio raised to the number of elements plus 1 all over 1 minus ratio. But because everything is raised to -1, then we get the reciprocal. As you may have noticed, because the system limit is now limited to k, therefore getting p sub 0 is harder. Why? Because instead of having a sum of an infinite series where the sum is simply 1 over 1 minus ratio, no? Your sum of a finite geometric series now is a 1 minus r raised to n plus 1 all over 1 minus r. And this is one of the reasons why, if you remember in the past lessons, I mentioned that if we can assume that the system limit, or if we can assume that the Q capacity is infinite, it is easier for us to model a problem, no, with a system limit of infinity, or without system limit. Now, because this is p sub 0, then we can get L. Sorry, p sub n. No? And p sub n is just this. Remember that the probability of having a state more than k is 0. Why? Because it is impossible for us to have more than k customers inside the system. Because once the system closes, we automatically reject any incoming customer. And the system only closes when we reach the system capacity of k. Now, because we have p sub n, then we can get L. L is by definition this, okay? And your summation, instead of running from 0 to infinity, we can limit it now to n equals 0 to k. Substituting p sub n, we get this. Now, I will just post the derivation of the formula for L. So please see the posted notes. And in this case, we end up with a value for L equal to lambda over mu minus lambda minus quantity k plus 1, the system limit, plus 1 times lambda over mu raised to k plus 1 all over 1 minus lambda over mu raised to k plus 1. Now, once you are able to compute for L, then you will be able to compute for W using Little's formula. No? And Little's formula states that W is equal to L over lambda bar. And remember a while ago, I said lambda bar is not equal to lambda. Why? Because, because lambda bar is the expected value of your lambda sub n's. So it's the summation of lambda n pn from n equals 0 to infinity. But remember, p sub n is equal to 0 from n equals k to infinity. Okay? And because this is 0 for n equals k to infinity, then the summation from 0 to infinity can now be reduced down to from the summation from n equals 0 to k minus 1. We factor out lambda because lambda is constant. We get this. And if you look at this is the sum from 0 to k minus 1 of p sub n. Therefore, this is easily 1 minus p sub k. Why? Because remember, the summation from n equals 0 to k of p sub n is equal to 1. Therefore, the summation from n equals 0 to k minus 1 of pn plus p sub n at k, so that's p sub k equals 1. Therefore, transposing to the right, we get this. And once we have our lambda bar to be equal to this, you can get your W. Once you get your W, you can get your WQ using this definition. And then finally, once you have your WQ, you can again use your lambda bar to get LQ. Now, for the MMSK model, so it's a variation of our multi-server queuing system, wherein your multiple server queuing system now has a system limit of k. What we need to do again is to draw our rate diagram. So the rate diagram for an MMSK model looks like this. So again, our states run from 0, 1, 2 until we reach a particular S, state of S, and then we continue until we reach the system limit K. The arrival rate, everything on top is still lambda. Your service rate increases until it reaches S. But once you reach S, your service rate now is constantly at S mu. Now, for this example, I will not be giving you a formula because for me, it will be harder for us to derive the formula and it will be easier for us to just do it manually. Now, what I will do is I will give you a very quick example on how to do this manually so that you will be able to understand how to how to do it on your own. So let's say your arrival rate is let's say 6 per hour. Okay, and let's say your individual service rate is 2 per hour, and you have um, 4 servers. Okay, and let's say your system limit is 6. So given the specific example, your rate diagram will look like this. So 0, 1, 2, 3, 4, 5, 6. Your arrival rate is 6 per hour. Your service rate will increase starting with 2 and then 4 and then up to 6. No? Once you, sorry, it will increase up to 8. And then once you reach 8, it will now be constantly at 8 because you only have 4 servers. So even if you have 5 or 6 customers, the number of busy servers is still 4. Therefore, your overall service rate is still 8. And we stop at state equals 6. Now, from here, the very first thing we need to do is to get our C sub n. No? Our C sub n cannot be written in a generic formula. So what I will do is I will list down every C sub n. So C sub 0 is equal to 1. C sub 1 is equal to 6 over 2. So that's 3. C sub 2 is 6 over 2 times 6 over 4. So that's 3 times 3 over 2. So that's 9 halves. C sub 3 is equal to 9 halves. So that's 6 times 6 over 2 over 4. So that's 9 halves times 6 over 6. So again, it's 9 halves. C sub 4 is 9 halves times 6 over 8 or 3 over 4. So that is a 27 over 8. C sub 5 is 27 over 8 times 3 over 4. So 27 times 3 is 81 and 8 times 4 is 32. And then finally, C sub 6 is 81 over 32 times 3 over 4. So 81 times 3 is 243 divided by 32 times 4 is 128. Okay? And therefore, to get P sub 0 is just the summation of C sub n from n equals 0 to infinity raised to negative 1. So this is equal to 1 plus 3 plus 9 halves plus 9 halves plus 27 over 8 plus 81 over 32 plus 243 over 128 raised to negative 1. Getting the common denominator is 128. So that is so 128, because that's 128 over 1 times 1, plus 128 times 3 is 384. 128 divided by 2 times 9 is 576, plus the same 576, plus 128 divided by 8 times 27 is 432. Okay? 128 divided by 32 times 81 is, again, 324. And then finally, this is 243. And then we raise everything by -1. So this is equal to 128 all over. Let me just add. So 128 plus 384 plus 576 plus 576 plus 432 plus 324 plus 243. So that's 128 over 2,663. Or roughly 0.0481. So the probability that there are no customers inside the system is around 4.81%. And because we now have P sub 0, which is equal to 128 over 2663, then we can get the rest of our P sub n's. So for example, P sub 1 is equal to C sub 1 times P sub 0. So this is equal to, if you get your C sub 1, that's 3 times 128 over 2663. Or in this case, this is equal to 384 over 2663. That's P sub 1. P sub 2 is equal to C sub 2, P sub 0. And that is equal to 9 halves times P sub 0. And if you multiply this, you will get a 576 over 2663. Now, you may want to notice that, look, P sub 1 is 384 over 2663. And when we were computing for P sub 0, 384 actually came out here, no? Where you were adding 3, no? And if you also noticed, P sub 2 is equal to 576 over 2663. 576 is here. In fact, if we follow the pattern, P sub 3, which is equal to C sub 3 P sub 0, and this is equal to uh, 9 over 2 times 128 over 2663. We don't need to compute again this because this is just 576 all over 263. If we continue the pattern, P sub 4 is equal to 432 over 2663. P sub 5 is equal to 324 over 2663. And then P sub 6 is equal to 243 over 2663. And all you have to do now, just to confirm if these values are correct, is to get the sum of your P sub n from n equals 0 to infinity and check if this is equal to 1. And you may want to just compute for it. If you add this, and this, you will actually get a sum of 1. Now that you have all of your P sub n's, no, so you have your P sub zeros to P sub 6, you can now actually get your L. L is equal to the summation of nPn from n equals 0 to infinity. And therefore, this is equal to 0p0 plus 1p1 plus 2p2 until plus 6p6. And this is equal to 80/70 over 2663, or roughly 3.03. So your L is this. In fact, you can also get your LQ. LQ, by definition, is the sum from n equals s to infinity of n minus s p sub n. And because s is equal to 4, so this is just the sum from n equals 4 to not infinity, but the system limit of 6, n minus 4 p sub n. So this is equal to, at n equals 4, this is 0. At n equals 5, that is 1p5, plus at n equals 6, this is 2p6. So this is just 1 times 324 over 2663 plus 2 times 243 over 2663. So this is 486 plus 324. So that's 0, 1. So that is an 810 over 2663. That is your LQ. And then from here, you can just simply get your lambda bar. Lambda bar is just, if you look at your rate diagram, your lambda are the same except for the last, because the last lambda is 0. And therefore, lambda bar is still lambda times 1 minus p sub k, or in this case, p sub 6. And once you are able to get your lambda bar, then from here you can get your W, which is equal to L over lambda bar. And then from here, you will be able to get your WQ, which is equal to LQ over lambda bar. And this is what I mean by manually computing for the 4 performance measures L, LQ, W, WQ, given an MMSK model.